Hello, my name is Diego, and today we will be doing the Kognity activity of projectile motion using this simulator. So, first we need to adjust the cannon to an angle of 50 degrees with an initial speed of 15 meters and just observe the overall trajectory of our golf ball, not our cannonball. There we go. We need to experiment a little bit with the launching angle until it hits this 15-meter mark. I found out that 70 is just the right spot when we have a 15-meter um, per second speed. Then, after we do these iterations and we find out this is the right angle, we are asked to calculate the time, the range, and the height of this trajectory. In this case, I got 2.87 seconds for the overall flight time, 14.74 meters for the range, and 10.13 rounded meters for the height. So let's fire it again and check it using this tool right here. So we have precisely 2.87 seconds on the time, 14.74 on the range meters, and on the height we have 10.13 meters. Here you can see what I did on my calculations on my iPad. So there you go. Basically using the different parts of uniform rectilinear motion and uniform accelerated rectilinear motion. Let's keep going. So we already calculated those three, and we can see on the spreadsheet that it is correct. Let's move on with the questions. Then we are asked, predict whether the trajectory of a cannonball will be different from the trajectory of a golf ball under the same conditions with no air resistance and explain our predictions. So, what is my prediction? There's no change at all when we do not have air resistance. Let's change it to a cannonball and a golf ball. And there we go. We see that there is no change. So, is the cannonball different? No, when there is no air resistance. Why? And we will be seeing that in the next question. It says, erase all the previous trajectory, set the type of projectile back to a golf ball. Let's apply, well, let's first fire it without air resistance. Then let's apply air resistance of 100 meters. Let's fire it. And we see some changes. Let's compare it to a cannonball with air resistance. And we see that there is pretty much no difference between the cannonball with and without air resistance, but there is a difference between the golf ball with and without air resistance. Why does this happen, and why is the golf ball, as it says here, why is it more affected by air resistance? Basically, when we have a heavier object, the air that's pushing it won't have a much of a significant effect as on a golf ball. A golf ball is lighter, thus the effect of air is going to be greater because of the difference in mass. So in this case, which is that difference? When we have air resistance, our range and our maximum height are going to be shorter. Take this parabolic shape, just shrink it a little bit. So we have a shorter range and a shorter height, as you can see here, shorter. So now that we've completed the points 6, 7, and 8, it's time to move on with 9. And, oh, we already did 9, sorry. We did the prediction of the cannonball with and without air resistance. And switching that off, we need to start experimenting with a independent variable and a dependent variable to see how everything changes depending on what we decide to modify. So as you can see in the next table, I wrote angles from 10 to 80, and I perform with the formulas that you can see right here on the top, the calculations for the range. I found out very interesting things. For example, complementary angles that add up to 90, for example, 40 and 50, 30 and 60, 20 and 70, and 10 and 80, have exactly the same range, and we can prove this. For example, let's take 40 and 50. So let's take 50 like this and shoot it. And then let's take 40 and shoot it again. And voila, we reach the same point, which is really interesting. If we were to plot those points into a graph of our dependent variable being the range, our independent variable being the launch angle, we found this very interesting shape. Is that a parabola, you may be thinking? No, it isn't. When plugging it into Desmos, we find out that the actual type of regression is that of a sinusoidal regression. What does this mean? That in here, we're going to be going from 0 to 90 in terms of our degrees, and we're going to be alternating between having, let's say, a positive range and a negative range. What am I talking about? Let's suppose for a second that we take our cannon and we elevate it. So now we're able to go from minus 90 degrees to 90 degrees. If I decide to shoot it like this, in any of these angles, I'm going to have a positive range because I'm shooting it this way. But if I, by some reason, were able to shoot it the other way around, like say more than 90 degrees, I would be going in the other direction, having, in this case, these negative parts of my negative uh, displacement on that x-axis. And we can clearly see that it's a sinusoidal function because it's going to be alternating between going one way or the other. We only have 360 degrees, so it wouldn't make sense to have more than that. It needs to be oscillating in this kind of wave. So basically, we found out that changing the angle represents a sinusoidal function, sine of x, with some changes into the graph. You can see it blocked in here, and you can also see it here. It's a perfect regression with a coefficient of 1, so it's perfect match. And I think it's something really pretty to be able to observe how having these complementary angles that add up to 90 will always have the same range. So for example, if we get a question where we're tasked of calculating the range at 10 and also at 80, we already know the answer if we just calculate it for one. Isn't that interesting? To me, it absolutely is. So, well, that was it. Thank you for watching, and we'll be seeing each other next time. See you.